Good morning, students. Now in this class, we are going to talk about I/O systems. It is fifth unit of operating system. Okay. See, whereas coming to I/O systems, generally management of I/O devices is very important part of the operating system. So we can say it is very important. So what will happen is it varies that the entire I/O systems, I/O subsystems are devoted to its operation. I/O subsystems must contented with two conflicts. We can say two conflict trends. So the first one is the gravitation towards a standard interface for a wide range of devices, making it easier to add newly developed devices to existing system. And the second one is the development of entirely new types of devices for which the existing standards interface are not always easy to apply. And next one is device drivers. Device drivers are modules that can be plugged into the OS to handle in a particular device, or we can say category of similar devices. Whereas coming to I/O hardware, see what is meant by I/O hardware. The I/O devices can be roughly categorized as storage, communication, user interface and others. And at the same time, device communication with the computer via signals sent over wires or through the air. At the same time, devices connect with the computer via ports. Ports is nothing but it is a serial port or parallel port. Next, coming to the common set of wires connecting multiple devices is termed as bus. See here definition of bus is, it is a common set of wires connecting multiple devices. Buses includes rigid protocols for the type of messages that can be sent across the bus and the procedures for resolving contention issues. Whereas next coming to here one representation, that is it will show the three of the four bus types commonly found in a modern PC. Okay, so that the first one is here, if you observe, means PCI bus, next one is expansion bus, next one is SCSI bus, next one is a DBSIT chain bus. Of course, the DBSIT chain bus is not shown in the figure here, whereas coming to first one is PCI bus. See, PCI bus connects high speed, high bandwidth devices to the memory subsystem and the CPU. Whereas coming to expansion bus, the expansion bus connects slower, low bandwidth devices with the typically deliver data one character at a time with, we can say, with buffering. Next time, SCSI bus connects a number of SCSI devices to a common SCSI controller. Whereas coming to next fourth one is DBSIT chain bus. Okay, so this DBSIT chain bus is not shown in the figure. It is when a string of devices is connected to each other like beads on a chain, and only one of the devices is directly connected to the host. So this is the representation of the various types of bus. Here, one way of communicating with the devices is through registers associated with each port. Registers may be 1 to 4 bytes in type and may typically include the following four, that is data in register, next one is data out register, status register, and next one is control register. See, what is meant by data in register? The data in register is ready by the host to get input from the device. Whereas coming to data out register, it is written by the host to send output. Whereas status is nothing but it has bits read by the host to ascertain the status of the device, such as it is in idle state or it is ready state for input, or busy, or error, or it can say transaction complete, etc. The next one is controls register. The control register has bits written by the host to issue commands or to change the settings of the device, such as parity checking, word length, or full virus, like that. Okay, there are the four types of registers. Okay, Next, coming to next topic is interrupts. Here, generally, interrupts allows devices to notify the CPU when they have data to transfer or when an operation is complete, allowing the CPU to perform other duties when no IO transfer needs its immediate attention. The CPU has an interrupt request line that is sensed after every instruction. Generally, a device controller raises an interrupt by asserting a signal on the interrupt request line, whereas the CPU then perform a save and a transfer control to the interrupt handler routine at a fixed address in memory. The interrupt handler determines the cause of interrupt and perform the necessary processing, perform a state restore and execute a return from interrupt instruction to return control to the CPU. Okay, this is the representation of the interruption. Okay, see here, first one is CPU, and then we have device driver initiates IO devices. Next one is CPU receiving interrupt, transferring control to the interrupt handler. Next one is interrupt handler processing data. Next one is CPU resumes. Again, it will go to the first one. Okay. Here, first and the second one is initiating IO device, and third one is input read out at the same time out complete. Okay. See here, first, second, third, second, and then third, fourth, and fifth, sixth, seventh. Totally 7 steps. Okay. This is the interrupts. Next one is coming to direct memory access. Okay. See here, whereas in direct memory access, for devices that transfer large quantities of data, such as the disk controller, it is wasteful to tie up the CPU transferring data in and out of registers 1 byte at a time. Instead of this work can be loaded to a special processor known as direct memory access, that is DMA controller. The host issue a command to DMA controller indicating the location where the data is located, the location where the data is to be transferred to, and the number of bytes of data to transfer. The DMA controller handles the data transfer and then interrupts the CPU when the transfer is complete. A simple DMA controller is a standard component in modern PCs, and many bus mastering IO cards contain their own DMA hardware. Handshaking between DMA controller and their devices is accomplished through 2 wires called as DMA request and DMA acknowledgement wires. Next one is, while the DMA transfer is going on, the CPU does not have access to the PCI bus, but it does have access to its internal register and primary and secondary caches. DMA can be done in terms of either physical addresses or virtual addresses that are mapped to physical address. The latter approach is known as direct virtual memory access, that is DVMA. Okay, and allows direct data transfer from one mapped device to another without using the main memory chips. Direct memory access by user processes can speed up operations, but it is generally forbidden by modern systems for security and protection reasons. Okay, here also we have totally first is device driver is told to transfer disk data to buffer the address X, whereas second one is device driver tells the disk controller, and next one is after the third one is disk controller initiate the DMA transfer, fourth one is disk controller sends the each byte to DMA, next fifth one is DMA controller transfers bytes to buffer X, next one is sixth one is when C equal to 0 DMA interrupts, then CPU to signal transfer completes. Okay, so this is a representation of the direct memory access. Okay, here direct memory access. Next, coming to next topic is application IO interface. Generally, user application access to a wide variety of different devices is accomplished through layering, that is different layers. And through encapsulating all of the device specific code into device drivers, while application layer are presented with a common interface for all devices. Okay, next two. Here we have different layers, that is here hardware, and next one is software. Kernel and the kernel I/O system, we have different devices here, keyboard, mouse, PCI bus, floppy disk driver, at the same time ATAPA devices. Next one is, if we initially we have SCSA devices. Okay, each and every device is connected to a controllers. That is, here the keyboard is connected to kernel I/O system to a keyboard device controller, whereas mouse, for that mouse we have mouse device controller. Whereas floppy, we have floppy device controller. Okay, the device controller is connected to corresponding drive. Okay, then we have kernel I/O system. Next one is kernel. Whereas coming to in this application I/O interface, we have block and character devices. Block devices are accessed a block at a time and are indicated by a B. That is, we are going to write letter B as the first character in the long listening on Unix system. Operations supported include read or write and seek. These three operations are it will support. At the same time, character devices are accessed 1 byte at a time and are indicated by C. Okay, letter C. In Unix long listening, supported operations include just get, put, okay, with more advanced functionality such as reading an entire line supported by a high-level library routine. Whereas next coming to blocking and non-blocking I/O devices. Whereas coming to blocking, with blocking I/O, a process is moved to a wait queue when an I/O request is made and moved back to the ready queue when the request completes, allowing other process to run in the meantime. Okay. Whereas second one is with non-blocking I/O. Non-blocking I/O, the I/O request return immediately whether the requested I/O operation has completely occurred or not. This allows the process to check for available data without getting huge complexity if it is not there. Okay. So, whereas coming to next one, one approach for programmer to implement non-blocking I/O is to have a multi-threaded application in which one thread make blocking I/O calls, while the other thread continue to update the screen or perform other tasks. Okay, so this is the blocking and I/O, blocking and non-blocking devices. Next, coming to next concept is kernel I/O subsystem. See, whereas in this kernel I/O subsystem, we are going to talk about I/O scheduling. Generally, scheduling I/O requests can greatly improve overall efficiency. Priorities can also play a part in the request scheduling. Buffering and caching can also help and can allow for more flexible scheduling options. On systems with many devices, separate request queue are often kept for each device. Here we are going to talk about buffering as well as caching and error handling. Whereas first one is buffering. Buffering I/O is performed for three major reasons. First one is speed difference between two devices. A slow device may write data into a buffer, and when the buffer is full, the entire buffer is sent to the fast device at all once, so that the slow device still has somewhere to write while this is going on. The second buffer is used, and the two buffers alternate as each becomes full. This is known as double buffering. Here, at the same time, second one is the data transfer size difference. Buffers are used in particular in networking system to break messages up into a smaller packet for transfer and then for reassemble at the receiver side. This is the second one. Next, third one is to support copy semantics. For example, when an application makes a request for a disk write, the data is copies from the user's memory area into a kernel buffer. Now the application can change their copy of the data, but the data which eventually gets written out to disk is the version of the data at the time the write request was made. So all these are the three buffering major issues. Okay. Next, coming to caching. So here caching involves keeping a copy of data in a faster access location than where the data is normally stored. Here next, buffering and caching is very similar, except that a buffer may hold the only copy of the given data item, whereas the cache is just a duplicate copy of some other data stored elsewhere. Next one is we are going to know about error handling. Here, error handling, in this error handling, IO requests can fail for many reasons, either transient, or we can say permanent, or we can say buffers overflow or disk crash. IO requests usually return an error bit indicating the problem. Unix systems also get the global variable error number to one of 100 or so well-defined value to indicate the specific error that has occurred. Some devices such as SCSI devices are capable of providing much more dedicated information about errors and even keep on board error log that can be requested by the host. Okay. So next, coming to the next topic, that is transforming IO request hardware. That is transforming IO request to hardware operations. So here what will happen is user request data using file names which must ultimately be mapped to specific blocks of data from a specific device managed by a specific device driver. Actually, whereas coming to DOS, that is disk operating system, DOS uses the colon separator to specify a particular device, whereas Unix uses a mount table to map file name prefixes to specific mounted devices, where multiple entries in the mount table match different prefixes of the file name. The one that matches the longest prefix is chosen. Unix uses special device files usually located in to represent and access physical devices directly. Each device file has a major and a minor number associated with it, stored and displayed where the file size would normally go, whereas the major number is an index into a table of device driver and indicating which device driver handles this device. Next, coming to the minor number is the parameter passed to the device driver and indicates which specific device is to be accessed out of many which may be handled by a particular device driver. Next one is a series of lookup table and mapping makes the access of different devices flexible and somewhat transparent to user. Okay, if you see the representation here, we have left hand side request IO and next one is system call. If it is can already satisfy the request, then it will go for. If it is yes, then what will happen? The kernel IO, we have kernel IO subsystem. Then here kernel IO system, what will happen? Transfer the data. Okay. Again, if it is no means, it will send the request to device driver, a block process if appropriate. And next one is process request, issue command to controller, configuring controller to block until interrupt, and next finally monitor devices interrupt when IO completes. Okay. After, if it is in the case of no, finally what will happen after performing the monitor device interrupt when IO completed, next it will go to the IO completed, generate the interrupts. Next from here, after completion of IO, after the completion of the IO completed, generate interrupt, what will happen? It will go to the, it will give the interrupt, that is receive interrupt, store data in device driver, buffer if input signal to unblock device driver. Next what will happen? Next we are going to perform in the determine which IO complete, which IO, that means what type of IO completed, indicating the state change to IO subsystem, then finally transfer the data, and finally IO completed, input data available, or we can say output completed. Okay. So in this way we are going to performing the various operations, that is transforming IO request to hardware operations. Okay. Right. Thank you very much.